We'll have a short class. So today we want to discuss something about what is called a standard form. This is not precisely the standard form, but this is for a 2-1 factor. So, I mean, this is not the usual, not precisely, usually the standard form. Standard form is, it is just a cyclic and separating vector. So I will define what is cyclic and separating vector. Then we will, I mean, it is just the usual GNS construction with trace. That will be the standard form for a 2-1 factor. So, and then we'll just discuss the Tomita-Takesaki theory, which is trivial for 2-1 factor, and we will just discuss that. So this is the definition. So M is a one-dimensional algebra. And the omega in H, a vector. Of course, we know this definition. It's cyclic. It says to be cyclic if you apply this M on this omega. You don't need to take the span, but I'm taking span closure equal to H. This is what is cyclic is. We have already seen this definition. And a vector, same vector omega, maybe need not be the same vector, some other vector, but I write it as the same vector. It's said to be separating for M. So if x omega equal to y omega implies x equal to y. So this just means if x omega equal to 0, then x is 0. That's what it means, of course. So proposition, actually just a remark actually. If, so we have M contained in P of H. Okay. Then omega in H is cyclic for M is equivalent to omega is separating for M prime for the commutator. Okay. The vector is cyclic for M, it is separating for the commutator. Okay. Proof. Of course, you can reverse M and M prime, it's the same thing. I mean, M equal to M double commutant. M is the commutant of M prime, so M and M prime you can exchange. I mean, you can flip, switch. So if omega in H is cyclic, for M, you want to prove that it is separating for M prime. Okay. So suppose X prime for X prime in omega in M prime, X prime omega equals 0, we have to prove X is actually 0. Okay. But this just implies X prime acting on Y omega or X omega equal to X prime omega, of course, because it commutes, which is equal to 0, of course. So this is for all X in M. But then this is dense. Okay. Dense. So as operator, X prime equal to 0. Hence separate. So, hence omega is separate for M prime. Okay. Okay, now the other way. So this is easy. Suppose omega in H is separating for M prime. So suppose omega is separating for M prime. Okay. Okay, we assume that. We want to prove omega is cyclic for that. Okay. So let H naught equal to take this closure. I mean, you don't need to take span. I mean, when you have a subspace, when you have even two vectors, you have to take the span, because m1 omega 1 plus m2 omega 2 it will appear. So you have to take the span. If it is just one vector, if you are applying, you don't need to take. That will be a vector space. So h naught equal to this. Okay. So let P be the projection. We want to prove omega, we assume omega is separating for m prime. We want to prove omega is cyclic for m. So we have this h naught. We want to prove h naught equal to h. So we want to prove this P is 1. This is the projection. We have to prove this is equal to 1. Now this is clear. Now we know, we have already seen this. P is in m prime. Now we know this. Okay. Okay. P is in m prime. And P omega equal to omega, right? Because P is projection onto this, because this is in h naught. Omega is in h naught. So P omega equal to omega. So which means 1 minus P omega equals 0. This is like 1 equal to P. Since separating. Okay. So it is just that, notice that the projection is in m prime. So 1 minus P is also in m prime. So this is so a vector is cyclic for m is equivalent to it is separating for m prime. Okay. So usually when we say something is in standard form, if there exists a omega which is cyclic and separating, but for our 2-1 factor, so this is the definition. For 2-1 factor, we assume that omega also gives a tracial state. Okay. So m contained in B of h is a 2-1 factor. Okay. We say m is in standard form. T. The thing is, I mean, the standard form is, I mean, a state need not be given by a vector state in the Hilbert space, but in GNS construction, it will be given by that. So, see, in general, if you have a one-Neumann algebra, it can be an abstract one-Neumann algebra, then you can embed it into B of h. We may even start with m in B of h, but then you can take copies somewhere, isomorphic copies somewhere else and work with that. So where that one Neumann algebra is sitting, that, I mean, that depends on the representation. Okay. And this m prime will depend on this representation. So m prime is something you want to standardly associate with m. Given m, you want to associate m prime in a unique way. So that is why we are taking this. Okay. So in general also, if even so, if there exists a omega h, which is cyclic and separating, both separating and cyclic. Separating. This is what usually standard form, but we assume something more, and because it's a 2-1 factor, we have a trace on this, and further this x going to x omega omega. This is a tracial. This is tracial. This is a tracial state. That is, of course, x y omega omega equal to y x omega. This is what tracial means. Okay. Mod of omega equal to 1, all that we have studied. Mod of omega. This gives a trace. This vector state gives a trace on this. So this is what we call a standard form. Okay. From here onwards, for this class, we assume m is in standard form. It's a 2-1 factor which is in a standard. We assume. Okay. Okay. So definition. Let m contained in B of h be in standard form. 2-1 factor, of course, this is 2-1 factor in standard form. So define J acting on X omega equal to this X star omega. This defined on a dense subspace, okay, for all X in M. This is defined on a dense subspace of H. Okay. Then, of course, then J is conjugate linear. J is antilinear or whatever. Conjugate linear. And on this dense subspace, J square equal to 1. Okay. So further, this is the proposition. Further, J extends to an anti-unitary. On H. By anti-unitary units, this is conjugate linear map. This is not a unitary, this is not a linear map, it is conjugate linear. It's clear, no? If you have an X star here, if you have a lambda here, it will come as lambda bar. So this is clearly a conjugate linear map. And clearly J square equal to 1. If you take star twice, then it becomes identity, okay, because it follows from the involution. So this is a J square equal to 1. It's a it's an idempotent and it's antilinear. And it will also be what is called anti-unitary. That is J, xi, J, eta. Unitary means this will be equal to xi eta. Here it will be the other way. That's all. Do you know example of an anti-unitary? You recall? Huh? It's going to H star. No, on a Hilbert space. Unitary we define on Hilbert space, no? Which is almost like identity here. This is like, a unitary which is also a positive, which is also, huh? In infinite dimension. Can you remember something? This is well-known thing. So, maybe from different Hilbert space, H to K or H to a different Hilbert. It's not different actually. It's when they are unitary, it's the same thing. But
if you take from H to going to the H star, as in X going to the
so H star by you mean the linear function. Good, correct. Yeah, H star. You said star. Sorry. Yeah. So good. That's what I meant. Yeah. So usually the Hilbert space dual is same as H. Dual of Hilbert space is itself, but it's not exactly itself. It is just the anti-unitary. It is just anti-isomorphic to that. So there is a conjugate linear map between them. So it is that's the standard example. You can take H and then H bar, which that's why it's called usually called H bar. You have called it H star or whatever, you can call it whichever. So that is the standard anti-unitary. In many places that will work. How it will work is, okay. The thing is, Hilbert, see, this is Van algebra in some situation, some specific situation. I said orthogonal comitant or a generalization of orthogonality. Okay. In that way, this J will take something to the opposite Hilbert space. This is the H star. In some vague explanation, it's okay. So anyway, so J extends to an anti-unitary. So that's what we want to show. Proof. We have to verify that it preserves the inner product on the same boundedness, everything, it's the same theory for antilinear operator also, conjugate linear operator also. You can see that the same idea, anything about bounded operators, the same idea works there. Okay, except that you have to do this. You have to flip the inner product. Okay, so we just want to verify this. We can verify it on a dense subspace. If it preserves the inner product on the dense subspace, then you can extend to an anti-unitary. It extends. That you can do. Do the same way. It extends to the completion or whatever closure. So if so, we just have to verify this. That's all. This is equal to X star omega y star omega, right? By definition. And that is equal to yeah. That is equal to, I mean, if you want, you can write it as trace if you want. This is just y x star, right? Trace y x star. I mean, this is the GNS thing is, so, I forgot to say, give an example. I forgot to say our gamma G is in standard form. I will come to this after this, okay? So y x star, and this is same as trace of x star y, which is same as you have y omega x, y star omega x omega, right? No, y omega, y omega. I mean, the trace of in the GNS representation, x, I mean, this is the GNS representation, no? X omega, y omega equal to y star x, trace of y star x. Okay? Right? This is the GNS representation. This is how it is defined. So it's the same thing. Okay? So this is equal to y omega x omega, and that is equal to this is right, no? X star omega. So this is right, and that's what we want. Right? So okay, it preserves the, it's not, doesn't preserve the inner product, it flips the inner product. Okay? So this implies Jx to anti-unitary, to an anti-unitary. In particular, it is bounded. Okay? This is because of the tracial property, otherwise this will not happen. Tracial property, you can flip it. It's very trivial. But in general, if you have some m sitting inside B of H, and if it is in standard form, whatever, if it does not satisfy the tracial property, if it has a cyclic and separating vector, still you can define this J or S or whatever. I assume that m omega is contained in H is dense. Okay? Then you can define a S, say S naught or something of x omega equal to x star omega. This will not be even bounded in general. Need not be even bounded. It will be an unbounded operator. Okay? So it's not simple for other von Neumann algebra. Only for 2-1 factor or a finite von Neumann algebra, this happens. Okay? Huh? It will not be bounded. Yeah. Extend what? Yeah, you can't extend now. When it is unbounded, you can't extend. If it extends, it will be bounded by whatever the theorem, open mapping theorem. Okay. Okay. So I forgot to say this example. Our gamma G, which is in B of L2G, G is ICC, of course, okay, infinite conjugacy class. Then this is in standard form. Of course, we defined our trace of x is equal to x of E1, E1. E1 is the orthonormal basis corresponding to the identity 1. This is the identity E1. And we have to verify that this E1 is cyclic and separating. Okay. Now, what is, if you have a x in gamma G, x E1, which is a vector in L2G, I mean, it's a vector in L2G. And if x E1 equal to 0, a vector, then you have that form, how you write this, how you get the matrix elements of this x, no? So that will all be 0, right? So by that prescription, x is equal to 0. I mean, once you know xe1, which is a vector in L2, that determines the operator. Okay, and if it is 0, then whatever the matrix element you are going to write, which is equal to x of, I mean, if this vector is some x vector, a xi vector, then that is going to be xi of x st inverse something like, st inverse something. Okay, because of that, x is 0. So this is clearly E1 is separating. Okay, so E1 is separating. Not all L2 vectors will not give rise to an element in this gamma G. I mean, a gamma G, if you apply it on E1, you will get an L2 vector that will determine the operator. There is no need that if you have some vector L2 vector that will give an operator. You can define a matrix element, but that has to be bounded. That you have to verify somehow. Okay, so that may not always happen. So for that, what we do is the following. So now to prove E1, which is in L2G, is cyclic. See, you have to only have to prove that by applying this gamma G, the M on E1, you get all finite vectors. I mean, vectors with finite coordinates. Okay? That you get it by applying finite matrices. I mean, you take any finite vector, if you have a xi in L2G, or if you want, I mean, you only have to get all this even 0. You have to prove that, I mean, to prove this is cyclic, you have to prove that you have to take gamma G, E1, and the closure span closure equal to L2G. This is what you want to prove. Okay. It is enough to get the orthonormal basis inside this. Span closure is this. And orthonormal basis EG equal to UG, EG equal to UG, E1. So you get all the orthonormal basis, so span closure will be there. So this implies E1 is cyclic. So you get all vectors if you take the span closure. So this is cyclic. Okay. Okay. So these are all just remark. So in general, so this is also says that this is a JNS representation also. And you can see that this standard form is unique. I mean, if you have a GNS representation for a given state, that is uniquely determined. Unique means up to unitary. So if you have another GNS representation, that there is a unitary between them, which takes the cyclic vector to the cyclic vector there, and it intertwines the operators also. Okay. So here it's a cyclic vector. It's also a trace. The state is a trace. Well, I have to say the trace is unique, which we have proved. But if you assume that this representation is unique, okay, the standard form is unique. Okay. So what is the remark? So I forgot. Okay, this is just maybe we can say it's a proposition. J x star J, okay, acting on y omega equal to y x omega. Okay, for all y. I mean, this is a vector in H. Y omega is a vector in H. This is a vector in H. So it is just the J x star J. J is an operator, x star is an operator. These are all operators. This is a vector. Because vector times omega. So J x star J acting on y omega is yx. This is like right multiplication. How is this M acting on this space? See, M is in standard form, M is in the GNS representation. The GNS representation, the operators in the C star algebra, any C star algebra, acts as left multiplication. So here also, if you have any vector x omega, if you have a y in the M, it will act as yx omega. Instead, you can apply y on the right. Okay, that is x omega going to, I mean, y omega going to yx omega. This is also an operator, which is densely defined. this need not be actually equal to, this need not be bounded in general. But since it is spatial, yx omega omega will be x omega omega. Okay. By that property, you can find that this will be actually bounded. Here in 2-1 factor, it will be bounded. If it's a left multiplication is how it acts, M acts. Right multiplication is also bounded. Right multiplication means y omega going to yx omega. This operator is also bounded. It will have the same now. Okay. But we prove that that is not, I mean, we need not check the boundedness. We prove that that operator is nothing but this, which is clear. You just apply, it will be clear. X star j acting on y omega equal to, of course, j acts on that, which is y star omega. Okay, then x star omega acting on j, which is, of course, which is equal to this. This is equal to y x omega, right? That's all. You just apply, you will get it. Just use the definition, you get it. So from this, I say that j x star j is in M prime. Is it clear to you? Why? J x star j is nothing but right multiplication by x. That is a bounded operator because it is composition of bounded operators. Of course, it coincides on the dense subspace, so it will extend and all that. Okay. I am saying that j x star j, which is an operator, is in M prime. Yeah. Correct. Yeah. 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 So all you are saying is right multiplication and left multiplication commutes. Why do they commute? No, it is just yeah, because it commutes. But why does it commute on left dense subset? It is associativity property. That's all. Based by associativity. I knew it's algebra, so it doesn't. I mean, you should remember that. I mean, we may use it, but algebra may not be associative. Sometimes, of course, in our case, we said, but it's granted. Okay? It's associativity. Okay, by associativity. That's all. So this is just vectors in M acts as right multiplication. What I have written? What is yx in M? For x in M. Okay. If if x in M. I'm confused about my own handwriting. Yeah. So if x is in M, then x acts as left multiplication, j x star j acts as right multiplication, and they commute due to associativity. Okay. That's all. Yes. It's just associativity. So this implies j m j. Of course, m x is there, x star is also there, so it doesn't matter. It's contained in M prime. Okay. So if you apply j, I mean, these are operators. You take all such operators, j, x, j, whatever, that is contained in M prime. Okay. You want to prove it is equal. Okay. So for that, we prove the following proposition. So omega in H, I mean, M contained in B of H is in standard form, is 2-1 factor in standard form. Okay. Okay. Then of course, omega is omega. I mean, omega is the cyclic and separating vector. Omega is cyclic and separating for M prime also, because we have proved cyclic for M, separating for M prime. So omega is in M is cyclic and separating. Separating for M prime also. Okay. So this is clear. So we prove the following. We have this operator J. For the time being, I put M also here to note that, I mean, it depends on M, right? We have used, I mean, it depends on the phenomenon. So I put the JM. I should have called it Jm throughout. Now I am calling, okay, Jm. So Jm, how does it act? Because this is also cyclic and separating. So you can consider this is also a representation of M prime also. M prime is also represented here. It sits here. So how does it act on? This is precisely x star omega. Jm of x omega is x star omega. That is how it is defined. Okay. Now Jm of x prime omega is also x prime star omega. This actually implies Jm equal to Jm prime. That's what it means, right? This is how Jm prime is defined. Okay. So if I prove Jm of x prime omega is equal to, see, omega is cyclic separating for M prime also. Okay. Now, if I prove this is what I want to prove. Jm of x prime omega is x prime star omega. The theory is beautiful, but the proofs are very simple. Okay. It's all, okay. Then Jm is equal to Jm prime. Okay. So that's what this implies. Okay. Further, this x prime omega going to x prime going to x prime omega okay, is tracial. Is a tracial state. So this says that is M prime sitting in B of H with omega, of course, is also in standard form. So M is in standard form. M as a cyclic and separating vector. And the same cyclic and separating vector is also cyclic and separating for M prime. Further, the same omega gives a vector state which is tracial for M, and it's also tracial for M prime. That's what this says. So I have to verify that how Jm act on x prime omega. Okay, Jm acting on x prime omega. I want to see what is it. So it's enough. I have to see how it looks on x prime x omega. Okay, you have to find to find the vector in a Hilbert space, you have to find its inner product on a dense subspace. This is a dense subspace. Okay, so this is for x in M. Okay, this is x omega, which is dense subspace. Now I want to flip the inner product. So for that I apply Jm here. The inner product will be flipped. Okay, so Jm x omega, Jm square x prime omega. Okay. If I apply this, the inner product will be flipped because J is anti-unitary. Okay. Now this is equal to, now Jm of x omega is x star omega. Jm square is 1. So this is just x prime omega. Okay. Now this is equal to omega. I can take x star here, x prime omega. Okay. Now this is same as, okay, let me write it, x prime x omega, because M and M prime commute. So this is equal to x, I bring it here, x prime star omega, x omega. So Jm of x prime omega is equal to x star omega, this, on a dense subspace. So this implies Jm of x prime omega equal to x prime star omega. Okay, that is Jm is equal to Jm prime. So now we want to verify it's a tracial state. So for that we have to verify x omega, x y prime omega omega. So this is equal to y prime omega x prime star omega. Okay. Just return it just like that. So this is equal to, I flip it and apply this Jm prime, Jm or whatever, doesn't matter, both are same. Jm of x prime star omega, Jm of y prime omega. I flip the product. Now this is equal to x prime omega, y prime star omega. Okay. Now this is equal to, I bring it here, y prime, x prime, omega, omega. So this is it. This is what ratio statement. So this implies omega going to, sorry, x prime going to this ratio on m prime. So m prime is also in standard form. That's what it is. That's all. This is Tomita-Takesaki. See, m prime, m contained in B of h is in standard form. So this is trivial theory, but this is what is called Tomita theorem for 2 factor. Then Jmj is equal to m prime. I mean, because J is same as Jm and m prime. So proof is just, we have that Jm, J subscript m, J, m is contained in m prime. We know that. And also J m prime, of course, this implies J m prime m, J m prime is contained in m. Okay. So you can apply the J here and you get it here. So this implies J m J, whatever, with m or without m, is equal to m. One way we have verified. For the other way, because the J is the same J, Jm and Jm prime are same. Because of that. Jm, then this is contained in this. Similarly, this is contained in this. Both are same. You can take this. So because of that, Jmj is equal to J prime. So this in particular imply corollary, m prime is also a 2-1 factor. Because it has a trace. Of course, if m is a factor, m prime is a factor. Right? Because m intersection m prime is the center for both of them. So it's a 2-1 factor. And m has a trace, m prime is also has a trace. M and m prime are isomorphic, not isomorphic. This is what is called anti-isomorphic. Okay, this is what I want to tell you. This is the anti-isomorphism is given by this, right? X in m going to m prime. That is, here it goes to j x plus j. Okay. This is an anti-isomorphism. You call it phi or something, then phi of xy is equal to phi of y, phi of x. It reverses the product. But it's a linear operator. This is not antilinear. X going to j x star y is not, it's linear. It's linear, right? Yeah. No, it's not linear, right? No, right? If you have a lambda, it will become lambda bar, that will become, it is antilinear, sorry. Yeah. And it reverses the product, yeah. Huh? That will be, yeah, that's right. No, it is linear, no. Jx star j is just right multiplication by x. So if you have a lambda x, it is just right multiplication by lambda x. So lambda can be taken out, right? It is linear. I don't know that's the problem. Okay. Jx star j acting on y omega is this yx omega. Okay. So if you insert a lambda here, lambda x, So this will come out as lambda only. So it's okay. So it's a linear operator, it just reverses the product. So it is the anti-isomorphism. So I will just tell you, just state this. In general, you can, if you have any M contained in B of H, with, this is for a general factor, with omega cyclic and separating. Then you can define a S naught like this. I don't call it J because J is called as something else. X star omega. If it's not a 2-1 factor, if it's not a finite factor, if the state is not the tracial state, then it need not extend to a bounded operator. So this will be mostly an unbounded operator. Even for B of H, it's unbounded operator. Even on B of H. B of H is not a finite factor. So in B of H is an unbounded operator. Okay. So, and it's, when you should work with matrices and see what it is. Okay, all these things. Okay, how it works in matrices and all that. Okay. Where you can, I mean, you can represent matrices on a B of Cn, tensor Cn, that is actually. Okay. So how the M comitant looks, and I mean, it's not full of them. I mean, see, if you have a matrices Mn, this will sit as operators in, usually it is in Cn, right? But the GNS representation will be Cn tensor Cn. So you will have a comitant is not Cn. So what is this theory for that you can check. Okay. So in general, you will have a S naught. This will be an unbounded operator. Unbounded operator also has a polar decomposition. Okay. That polar decomposition will have a J, give rise to a J, that will be anti-unitary. That anti-unitary will satisfy the same problem, same property. J will be equal to M prime. But you will get another one, another delta, J delta equal to S naught. I mean, this is not S naught is not the operator. You will have an S operator because in unbounded theory, you can close an operator. Okay. This will not be, see, there is something called a closed operator. Closed operator means the graph should be closed. Of course, it will not be defined on all of H. If it is defined on all of H and the graph is closed, then it is a bounded operator. So that will not happen. If it is not defined on a whole of Hilbert space, then it may not be bounded. It can be unbounded, it can have a closed graph. So the S may not have a closed graph. So you had the S naught, which I defined here. This may not have a closed, this may not be a closed operator. You close it. You can closure, you can take a closure of an operator. That will be S. I'm just vague, I'm not defining anything. Okay. You close means you take the graph of an operator. You know what is a graph of an operator. You take the closure of that. So that will give an operator. So that will be the closure of S. Okay. So that will have a polar decomposition like this. Closed operator will have a polar decomposition like this. This will be an anti-unitary. This is because it's anti-unitary, this anti-unitary. This will be a genuine unbounded operator. Okay. This unbounded operator will give, if you have an unbounded operator, it's like you can apply bounded function to get a bounded operator. Okay, an unbounded operator. So you can apply this theta IT. This will induce an automorphism of M. I mean, this theta IT this will be a unitary. Okay, and this unitary will induce an automorphism of M. And that is the Tomita-Takesaki theory. That will have some property, and that is what the theory is. So it's as you can see, it's unbounded operators coming in, and it's all very proof and everything will be very messy. That's stop.